This unit starts us on 2.3, so we're going to be moving away from just quadratics, which are x squared, ax squared plus bx plus c, and moving on to higher number polynomials. Okay, so we're going to be able to identify these polynomial functions. Our goal at the end is basically to graph them, and everything we're going to do in this unit is working towards graphing a polynomial. Okay, the general form of polynomial function is going to be this thing where we have a sub n x to the n plus a sub n minus 1 times x to the n minus 1, etc., all the way down to a sub 0 x to the 0. Okay, so all these are just x to some exponent. The largest exponent in this list is what we call the degree of the polynomial. In front of that, x to the n or whatever is a coefficient. And we don't use a, b, c, d letters like ax squared plus bx plus c anymore, only because we don't really know how many numbers or how many letters we're going to need. Because n could be any integer or 0. Okay, it could be a large integer, as large as 102 or 76 or 5,000,000,002. Okay, so at that point we're going to run out of letters, so instead we just number the coefficients. A1 goes to x1, A2 goes to x2, A3, A4, all the way up to a to the n, whatever n happens to be. Okay, the largest n in the list is what we call the degree of the polynomial, and the coefficient in front of that n, x to the n, or a sub n, that's going to be our leading coefficient, okay? That's what we call the leading coefficient. And the two of these, degree and leading coefficient, tells us a lot, quite a bit actually, about our polynomial. Okay, so before we move on, there's a couple of properties of polynomials that we need to be aware of. The first is that a polynomial is always going to be smooth, meaning there are not going to be any sharp breaks. Like in the picture in the lower right-hand corner, okay, that one has several sharp breaks, okay, 3 sharp breaks. Okay, it has one here, okay, and it has one here. Not quite so obvious, but this is also a sharp break right there. Okay, and so those 3 sharp breaks mean that that's not going to be a polynomial function. In fact, that's probably going to be a situation where it was a piecewise function. Okay, because that's the situation on the second graph over here. Okay, that's a piecewise function that has 2 parts to it. Okay, and so that's the other aspect of a polynomial function. It's always going to be continuous, meaning that I can draw it from one end minus infinity to the other end without lifting up my pen or pencil. Anytime it's going to have an open circle in this, it's not a polynomial. Okay, so those are 2 properties of polynomials, and that's going to lead us towards being able to graph a polynomial. So first off, what happens at the ends of the graphs, at really large numbers of x and at really large negative numbers of x? Okay, we describe that as saying like x approaches infinity, or x gets bigger and bigger until it gets towards infinity or minus infinity. Okay, and so what happens is going to be based on the leading coefficient and the degree. Okay, because the value of the leading coefficient and the degree of the polynomial determine whether it goes to plus infinity, the range or y, f of x, does it go to plus infinity as x gets bigger, or does it go to minus infinity as x gets bigger? Okay, so 2 possible conditions for the degree. Okay, the degree will either be even or odd. If it's even, let's take x squared as an example, okay, then a positive leading coefficient means the ends of the graph go upwards, okay? So if this was my graph, it means that my ends of the graph would go upwards like this. Why does that keep popping up? Okay. Okay, and if the leading coefficient happens to be negative, then the ends of my graph go downwards, okay, like this. Okay, so that's what happens when my degree is even. Okay, taking a page from Dr. O's lessons, okay, he had this situation where you went faster, faster, slower, slower. We're going to do the same thing here, okay, except in our case, it's even, even, odd, odd, because when we have an odd degree, like x cubed, okay, then a positive leading coefficient means the right end of the graph goes up, but the left end goes down. So this is a graph of x cubed, Okay, and as you can see, on the right-hand side it goes up, and on the right-hand side it goes up, and on the left-hand side it goes down. And if the leading coefficient happens to be negative, a sub n is negative, then the left end of the graph is going to go up, but the right end goes down. So again, using Dr. O's method, it's going to be even, even, odd, odd. Okay, and it shows you which direction the ends of the graphs are going to be going. Okay, so this is a problem that you can do for practice. It's out of the textbook, so if you're following along at home, you can do that at home. I'm not going to do it here on the videos. You could always pause it and try it on your own. Okay. Here's another function that you could try. Okay. In this case, minus 4x cubed. What do the end behavior of the graph look like? Okay. In the given picture, okay, which is x cubed plus 3x squared minus x minus 3, it goes up on the right, down on the left. My degree is 3, x cubed. The leading coefficient is plus 1, and so it's going to be up on the right, down on the left. Okay. And for the next one, you shouldn't have to multiply that thing out to find out what the leading coefficient is. Okay, because you know what all the x's are going to turn out to be. And when you multiply it out, all you care about is what the degree is. In this case, my degree would be 6, 3 plus 2 plus 1. And my leading coefficient would be minus 4 times 1 times 1, or just minus 4. Okay, so that gets us the end behavior. Now we're going to worry about what happens. Where does it cross the x-axis? Okay, because where it crosses the x-axis is basically saying, where is f of x equals 0? We normally call this the zeros of a polynomial function, or a lot of times we'll also call it the root or solutions of f of x. And this is where I'm going to remind you about different ways I can factor a cubic. Okay, we can factor by grouping, and we can also factor by using the SOAP method, which is same, opposite, always positive. Okay, it might help for you to review those two methods from chapter P. Okay, again, here's a problem you could practice. It's out of the textbook. You can follow it there. I'm going to skip it. Okay. But if I look at this function, minus x to the fourth plus 4x cubed minus 4x squared, it simplifies to minus x squared times x minus 2 squared. Okay, and it's easy to find the roots in this case, okay? The roots of this equation are x equals 0 and x equals 2. But a function of x to the fourth should have 4 roots, okay? You'll always have a root equal to the degree. The root may be imaginary, but you should have a root for each one. Okay, but in this case, I only have 2 roots. But the reason I only have 2 roots is because those roots actually occur twice each. X equals 0 occurs twice because I have x squared. And x equals 2 occurs twice because it's x minus 2 squared. And so that square is what we call the multiplicity, because it could be any other integer. It could be x minus 2 cubed or x minus 2 to the fourth. Okay, and when it's an even multiplicity, it means that the graph will touch the 0 and then change directions. So that would be a situation that looks like this. Okay, it touches the 0 and then changes direction. An odd multiplicity means that the graph touches 0 but continues through the x-axis. So it would be something like this. Okay, it continues through the x-axis. If it happens to be a larger multiplicity than 1, it gets to look something more, let's see if I can erase this. Okay, it'll look more like this. It flattens out in the middle. And the flatter it is, the larger the odd multiple happens to be. To be honest, we're really going to stick with 3 as the largest possible odd multiplicity. Okay, in terms of trying to read from a graph. Okay, so how does this multiplicity work? Whoops. Okay, so for practice, find the zeros and multiplicity of this. okay, and then sketch a graph of f of x. Okay, I'm not going to go into this. Again, this is something that I did do in class, but it's in the textbook. Okay, moves us to the intermediate value theorem. Okay, this also gets into finding zeros. Okay, the intermediate value theorem basically says if on one side f of a it's a negative, okay, is below the x-axis, and f of b is above the x-axis, it's positive, then there has to be a zero somewhere between a and b. Okay, which makes sense because my graph is smooth and continuous. There's no breaks. I can't go from a negative number to a positive number without touching zero. Okay, that's all the intermediate value theorem is saying. Okay, again, practice. Okay, in this case, I don't really want you to find the zeros. No, nothing about this question says find the zero. All it says is show that the polynomial function has a real zero between x equals 2 and x equals 3. So calculate f of 2 and calculate f of 3 and see what those values are. If one is positive and the other one is negative, there has to be a real zero somewhere between them. Okay, so that brings us to turning points. Okay, turning points is wherever we ever have a minimum or a maximum in my graph. Okay, and the degree of a polynomial also tells us how many turning points we could possibly have. It tells us the maximum number. Okay, because if you think of x squared, it's a parabola. It has one turning point. Okay, so a polynomial of degree n has at most n minus 1 turning points in its graph. Okay, this is a maximum. The graph could have less, like the graph of x cubed actually has 0 turning points. It has no local minimum or maximum. Okay, and going the other way, if I have a graph and the graph shows m turning points, then the polynomial must be at least of degree m plus 1. It could be larger because of that multiplicity aspect. Okay, but it has to be at least of degree m plus 1. And so this gets us into how we can go from a polynomial function to a graph. Okay, the first thing you really want to do is use the leading coefficient test to determine the graph's end behavior. We're just going to label the graph, okay, put an xy coordinate and say, is it going to go up on this side or down on this side? Okay, then we'll go about finding x-intercepts by setting f of x equal to 0 and solving the resulting polynomial equation. Okay, paying attention to our multiplicities at this point, okay? Because if I have an odd multiplicity, it's going to cross the x-axis. If I have an even multiplicity, it's going to touch the x-axis and turn around. Okay, so we need to pay attention to the multiplicities. The third thing we're going to do is find a y-intercept by computing f of 0. So this gives us multiple points for us to graph and at least sketch through that. Okay, and then we're going to use the fact that the maximum number of turning points is n minus 1 to check whether our graph kind of makes sense. If I end up with too many turning points, I need to go back to the drawing board. Okay, symmetry may also help us to draw a graph in that if I know one side, it'll be similar to the other side. So remember, even symmetry, if all my exponents are even, x to the second, x to the fourth, x to the sixth, x to the 0. If those are all even, then it's going to be symmetric over the y-axis. If they're all odd, 1, 3, 5, 7, etc., then it's going to be an odd function and it's going to be symmetric over the origin. So flip it over the x-axis and then flip it again over the y-axis. Flip it over the y, then flip it over the x. Okay, so that's basically the lesson associated with 2.3. Okay, understanding what the leading coefficient test is, and then what the multiplicity is, and how we can use those to help draw our graphs. Okay, thank you.